Good afternoon. Welcome back to Codex. Many, but not all, of our talks this summer feature graduate students and postdocs who were nominated to speak by their senior colleagues. Today, we're very happy to have Dr. Nadiia Derevianko be the next speaker in this series. Nadiia is currently a postdoc at the Georg August University in Göttingen, working with Professor Gerlin Plonka-Hoch. She graduated from the National Academy of Sciences in Ukraine in 2015 under the direction of Professor Anatoly Romaniuk. Nadia's research is in signal and image processing, and we're very happy to have her here today to tell us about estimation of signal parameters by iterative rational approximation. Take it away, Nadiia.
So thank you for the introduction. Thank you also very much for the invitation. My talk will be based on my recent joint research with Professor Gerlin Plonka-Hoch from Universität Göttingen and with her PhD student Markus Petz. So I would like to start my talk with short motivation of our research. So let us have the function 1 over t, and this function can be represented using the following integral. So from this integral representation, we can assume that this function 1 over t can be very good approximated by exponential sums. And this question is actually very well studied. And with this function, we are in the real setting. So parameters lambda j and gamma j that determine this exponential sum, they are real. And it is also known that the following arrow in the space n infinity in the maximum norm decays exponentially. And therefore, when we deal with this very simple function, it is enough to consider approximation by short exponential sums. So when m order of this exponential sums is small. Now we consider more complicated oscillatory functions. So we take first the Bessel function of the first kind, of the first type. So we consider this function on the segment 0, 1, but we take the scaling factor 100 pi. And this Bessel function can be, for example, defined by the following series. And it is not so obvious in this case, but this Bessel function can be also very good approximated by exponential sums. But since we deal now with a bit more complicated function, and therefore, in order to achieve also good approximation error, we need to take more terms in this exponential sum. For example, in order to achieve the error 10 to the power minus 11, we need to use 28 terms. And in this case, with this function, we are already in the complex setting, and we know that coefficients gamma j and parameters lambda j are complex now. And it is even known that these nodes, e to the power lambda j, are located inside of the unit circle. And now we consider the last example. So we take this Dirichlet kernel. So this function is very well known in the theory of approximation of periodic functions. And this function is also periodic. So we consider the Dirichlet kernel of the order 50. So, and we take only half of the period here. And this function can be also very good approximated by exponential sums. And if we want to achieve the error 10 to the power minus 13, we use now 44 terms in this exponential sum. And we are also in the complex setting now, but this case is even more complicated because now the nodes e to the power lambda j are located inside and outside of the unit circle. So from these examples, you can see that this is that sometimes we need to study for some applications. We need to study this complex exponential sums. So when nodes e to the power lambda j are located not only unit circle that is considered in the harmonic analysis, but these nodes have different locations. So they can be located inside of the unit circle or outside, or they can be even real. And coefficients gamma j are also complex, and we assume only that these coefficients does not equal to 0, because then we just do not have this term here. And we assume also that parameters lambda j are pairwise distinct, and we say that m is the order of this exponential sum, and we consider finite exponential sums. So now I come to the outline of my talk. So my talk will have the following three main parts. So we study this exponential sums, and first of all, we study the question of reconstruction of this exponential sums. And we develop a new algorithm for the recovery functions of this form, and we call this algorithm ASPIRA. It states for estimation of signal parameters by iterative rational approximation. And the main idea that we use in this algorithm is that the Fourier coefficients of these functions have a rational structure. And we go to the Fourier side and we reconstruct this rational structure with already known AAA algorithm. So I will explain further in my talk this AAA algorithm also. And further, we can also show that our new ASPIRA algorithm is very much connected to known Prony-type algorithm. And actually, ASPIRA can be described as a matrix pencil method. That will be the second part of my talk. And in the end of my talk, I would like to show you some examples. So our new ASPIRA algorithm especially works very good for the reconstruction of noisy data. And I also would like to be back to these three special functions that I showed you in the beginning of my talk, and to show you that we can also apply ASPIRA for the construction of exponential sums of good approximations, at least for these three special functions. So now I would like to mention also some related research. So this question of reconstruction of exponential sums is very well studied, and the Prony method is probably the most famous known method, but it is also known that the Prony method is not very stable, and therefore in these days we use also improved Prony methods, for example, ESPRIT method or matrix pencil method. And further in my talk, I will also speak about these two Prony-type algorithm. And I also like to mention the following two related publications. They are also related in some sense to our research. So Prony-type algorithm can be also used in a Fourier domain in order to get rational approximation in time domain. And the idea that we use in our research is somehow converse, because we apply a rational approximation in the Fourier domain, and we get reconstruction of exponential sums in time domain. So now I will consider that main property that we use in our new ASPIRA algorithm. So we have this exponential sum. So we put 2 pi here just for convenience, and we have this new restriction now. So it means that this exponential sum at the moment does not contain one periodic components. And we take only one component, and we expand this component in the Fourier series on the segment 0, 1. And CK are coefficients of this expansion. So we further compute these coefficients. So we find that actually these coefficients can be found by the following formula. And this formula has a special structure. So it is a rational function with respect to parameter k, where k is the index of Fourier coefficients. And so we can say that these Fourier coefficients can be represented via some rational structure. And in the same way, we can also compute Fourier coefficients of all components in this exponential sum. And in general, we can write the following formula for the Fourier coefficients of these functions of complex exponential sums. And we can conclude in the end that Fourier coefficients of exponential sums have a rational structure. And we want to reconstruct this rational structure. But we will use this property not in this form. We will go further to DFT coefficients because it will be more convenient for applications. So we have this exponential sum, and we will speak about reconstruction of these parameters lambda j, or it is the same somehow that to reconstruct nodes zj, because this is only the question of one logarithm. And first we will assume that exponential sum does not contain nodes of the following form. So there are no these roots of unity at the moment. But further we will also include these nodes of this special form. So we have 2n samples. It is input information for the algorithm, 2n values of function f at integer points. And we compute DFT coefficients by the following formula. And we see that these DFT coefficients also have a rational structure. So there is a rational function that represents this DFT coefficients. And now we want to define this rational function. So we denote this function like Rm, and we defined it in the following way. So we have Zj, we take this Zj from the denominator, and you see this is exactly our nodes that we have in definition of exponential sum. And now we defined coefficients Aj, and this is so we take these coefficients from nominator, so they are defined by the following formula, and this rational function has a type m-1m. So it means when we represent this rational function in other form, like a quotient of two polynomials, then nominator, it is polynomial already, it has degree m-1, and denominator has degree m. And further, we define also the following 2n special points. It is roots of unity. And from this formula, you see that this rational function Rm interpolates this modified DFT coefficients at these 2n points from the unit circle. And now we will work with this rational function Rm, and now our goal is to reconstruct this rational function, because it is the same that reconstruction of exponential sum. So when we find the type of this rational function m-1m, it means that we will get immediately order of the exponential sum m. So then when we find this Zj, they are poles of this rational function. So we have immediately nodes of the exponential sum. And then we compute coefficients Aj, and having these coefficients, we will find the coefficients gamma j from the definition of exponential sum. And to reconstruct this rational function Rm, we need to find a good algorithm for rational approximation. And so we use the following AAA algorithm that was recently developed in the paper of Nakatsukasa, Zete, and Trefezen. So this is algorithm for the construction of rational approximation. And we use this algorithm on the Fourier side. So this algorithm works in the following way. So we have this input information. So we have 2n complex points, And we have 2n samples, 2n values of function g at these 2n points. And g, it is that function for which we want to construct a rational approximation. So this AAA algorithm construct a rational approximation for function g with this given in advance tolerance. So, and this AAA algorithm combines the following two main ideas. The first main idea it is that this algorithm constructs a rational approximation in a barycentric form, and that ensures stability of this algorithm. So it is a rational function of the following formula, and in this formula, Wj are weights, and these weights are computed during the algorithm as a solution of some least squares problem. And then we have here exactly m points. They are also chosen during the algorithm in some adaptive greedy way. And we also have the corresponding samples. So it is values of function g at these endpoints. And the rational function in this barycentric form has a type m-1, m-1. And also what is important that when we have this rational function in this form, then it interpolates the function g at these m points that we use for the construction of this barycentric form. And the second main idea of this AAA algorithm is that this algorithm works iteratively. So we start with a rational function of type 0, 0, and that is actually the constant. And then we enlarge a type of constructed rational approximation until we get until we achieve this given in advance tolerance. So when this AAA algorithm stops, we have the following output information. So we have m, it is number of iterations, and we have this three sets of values. Using them, we construct a rational function in this form, and we know that this rational function approximates function g in the following way, that the error is smaller than tolerance. And we also know that this rational function interpolates function g at this endpoints. So I will not go further into details about this AAA algorithm, but I just want to show you how we use this AAA algorithm for the reconstruction of function RM. So about this function, just want to remind you that we know the following. We know that this function has a type m-1m, and we know that it interpolates modified DFT coefficients at these two endpoints from the unit circle. So we apply AAA algorithm with the following input data. So we take tolerance 10 to the power minus 13, and we have this set gamma. It is exactly this two endpoints from the unit circle. And we have this set G. It is this modified DFT coefficients. And this input data come from this interpolation condition that we have. And then AAA algorithm constructs for us some rational function R after a certain number of iterations, such that the following inequality holds. But since we have this a special case, so we deal with this special rational function. So we have we have even more. So in our case, AAA algorithm works according to the following theorem. So we have exponential sum in the following formula. And we have 2n samples. It is values of function f at integer point, and m it is the order of the exponential sum. M is smaller than n, and we compute this DFT vector. So we need this DFT vector for AAA algorithm. And then AAA algorithm terminates after n+1 steps and takes n+1 interpolation points. So where m, it is the order of this exponential sum. And we know that rational function Rm is reconstructed exactly. And we know that we have not only n+1 interpolation condition that is given already in AAA algorithm, but we have all 2n interpolation conditions here. So when AAA algorithm stops, we have not this inequality, but we know that this difference already equal to 0, because AAA algorithm constructs for us exactly this function Rm, but in other form, in a barycentric form. And now having this barycentric form, we have to reconstruct this fractional decomposition representation form. And here, I also would like to notice when AAA algorithm stops, so we know that it stops after n+1 steps, so we can already reconstruct m. So it is number of iteration steps minus 1, so the order of the exponential sum. And now we will speak about that, how using this barycentric form for rational function, we reconstruct this other form, fractional decomposition representation form. But I also would like to notice here that we need to have a function Rm of type m-1m. But as we already know, a rational function in this barycentric form has a type mm. And this is also that we prove in this theorem that Rm is reconstructed exactly. That actually in our special case, this rational function in this barycentric form has not a type mm, but m-1m. So now we go to the reconstruction of these parameters aj and zj. So we know that zj are nodes, are poles of this rational function in this barycentric form. And these poles can be found in the following way as eigenvalues of the following generalized eigenvalue problem. And this actually was already known. It can be found also, for example, in the paper of Nakatsukasa et al. And we also use this idea. And then when we have zj, we can reconstruct coefficients aj, solving the following system of linear equations with respect to parameters aj. So this system comes also from our theorem, because we know that we have this 2n interpolation conditions, and in other form they can be written like this. Or we can also write this system of linear equation in a matrix form when we define the following Cauchy matrices. And now we can already formulate the main steps of our new ASPIRA algorithm. So ASPIRA, it states for estimation of signal parameters by iterative rational approximation. And we take input data, it is 2n samples and tolerance that we need for AAA algorithm. So first we compute DFT vector. We also need it for AAA algorithm. And then using this AAA algorithm, we compute a rational function Rm in a barycentric form. And then we reconstruct fractional decomposition representation form of this rational function. It means that we find these parameters aj and zj. And this m is found as a number iteration steps -1 in AAA algorithm. And now the question is whether we need the nodes zj, or we can also find this parameters lambda j, taking just one logarithm, and coefficients gamma j are constructed using this formula. And here I also would like to do one remark. So ASPIRA algorithm looks in the following form when we do not have nodes of this form, this 2n roots of unity, because when we assume that this exponential sum contains also nodes of the following form, then the corresponding components lose the Fourier coefficients or DFT coefficients of the corresponding components, lose the rational structure. And we cannot use this AAA algorithm because we don't have a rational function anymore. But we also know that only the finite number of Fourier coefficients or DFT coefficients lose this rational structure, and therefore nodes of this form can be reconstructed in a post-processing step. So our algorithm also works for the components with the following nodes. But further, I would like to go to the second part of my talk, where I will speak about a connection of our ASPIRA algorithm to known Prony-type algorithm, and we will formulate a ASPIRA 2 version. And in that case, it does not matter whether we have nodes of this form or not. So therefore, I will not go into details about this special case here. So now we will speak about a connection of our ASPIRA algorithm to known Prony-type algorithm. And at this point, I would like to mention the following paper of Daniel Potts and Manfred Tasche, where they offered a unified approach to this Prony-type algorithm. And here I will speak about matrix pencil method and ESPRIT method. So we use again, as given information, 2n samples, and now we have one parameter L. It is a new parameter L. It is upper bound for M, for the order of the exponential sum. So we don't have this parameter in our ASPIRA algorithm, but it appears in this Prony-type algorithm. And we define then 3 Hankel matrices. So we define one large Hankel matrix where we use all given samples from F0 to F to n-1. And then we define also 2 smaller Hankel matrices. So we obtain H0 from H when we remove the last column, and we will get H1 from H when we remove the first column. And so now, using these 2 smaller Hankel matrices, we define the following matrix pencil. So Z is a variable, complex variable here, and the problem of finding of eigenvalues of this matrix pencil is called generalized eigenvalue problem. So we already had this once when we considered the question of finding poles of a rational function in a barycentric form, and we will have also generalized eigenvalue problem in this Prony-type algorithm. So now we speak about that, how these exponential sums are reconstructed using a Prony-type algorithm. So M, the order of the exponential sum, comes as a numerical rank of this large Hankel matrix, and then Zj, nodes Zj, they are eigenvalues of the following generalized eigenvalue problem, or they are eigenvalues of the following matrix pencil. And this is also the reason why this algorithm is called matrix pencil method, because we deal with this matrix pencil here. And then when we found Zj, we can find the coefficients gamma j, solving the following system of linear equations. And this system can be also written in a matrix form, where V, it is van der Monde matrices here. So this is main steps that we use in the Prony-type algorithm. And further, I would like to show you that we can describe our ASPIRA algorithm using almost the same three steps. And the only one difference will be how we find M, and also that Zj will be eigenvalues of a bit different generalized eigenvalue problem. So instead of Hankel matrices, we will use so-called Lowner matrices. And now I would like to be back again to this AAA algorithm. So this AAA algorithm works iteratively, and at each iteration step j, it constructs a rational function in a barycentric form such that this rational function interpolates modified DFT coefficients at j points from the unit circle. And then, so we have gamma, it was like a given set of points in the beginning for us. And now we have this interpolation condition. So we can divide gamma for two subsets. So Sj, it is points that we use for interpolation here. And then gamma j, it is the rest. We can also say that we use them further for approximation in the algorithm. And now using these two sets of points, we define these Lowner matrices in the following form. So we take columns using, so we create columns using this, these points that we take for interpolation, and rows we take points from the set gamma j, this point that we use further in the algorithm for approximation. And we compute at each iteration step these Hankel matrices, but we know that we have only m+1 iteration steps, so we have not more than m+1 columns here. And then at each iteration step of the algorithm, we also have to choose this weights wj. And further, I would like to show you how we do it. So this vector, weight vector w, is chosen in the following way. And this matrix problem can be solved like this. So we compute SVD of this Lowner matrices, and the w is a singular vector that corresponds to the smallest singular value of this Lowner matrix. So further, we will deal with these Lowner matrices, and these Lowner matrices, they appear inside of this AAA algorithm when we want to find this weights wj for this barycentric form. And further, I will take the Lowner matrix that is created in the last iteration step of the algorithm at the step m+1. So it is the biggest Lowner matrix that we have. And then we show that there is a connection between Lowner and Hankel matrices. So here we take this Lowner matrix that is created in this last iteration step of the algorithm. And here we have exactly that large Hankel matrix that we use in Prony-type algorithm. But when order of exponential sum is known in advance, because as I already said, in ASPIRA, we do not have this parameter L upper bound for exponential sums. And here we have this special two matrices Q. So these two matrices have a special structure. And further, I would like to explain you some properties of these matrices. So in order to understand better the structure of this matrices Q. So we need more definition now. So Q is some polynomial, and U is the vector of roots of this polynomial. And then QUL is the same polynomial, but just without one root UL. And now we take two different vectors, U and Z. So you see that U, it is a vector created from these points that, from these two endpoints that we have in the beginning of AAA algorithm. So this is two endpoints from the unit circle. And Z, it is a vector of nodes that we have in the exponential sum. And then when we multiply these two matrices, then we will get the matrix of the following form. And when we assume that Z and U are equal, so it is the case when nodes coincide with these two endpoints from the unit circle, then this multiplication will have the following form. So we have only entries on main diagonal and all other entries equal to 0. So we can say that this matrices Q diagonalizes van der Mon matrices. And now, having this factorization, we can also show that the following factorization is also true for two smaller Lowner matrices. So now we define these two Lowner matrices L0 and L1. So this is matrices that are created at the last but one step of AAA algorithm. So we have in general n+1 iteration steps. And so this matrix, this Lowner matrix is created at the step n+1. And these two Lowner matrices are created at the step m. And we can show that these two matrices also have similar representation. But here we use already this two smaller Hankel matrices. And now, using this representation for Lowner matrices, we can show that our ASPIRA algorithm can be reformulated as a matrix pencil method. And the main idea is that now nodes Zj will come as a solutions of as an eigenvalues of the following matrix pencil. So it is the same that we have for Prony-type algorithm, but we use here Lowner matrices instead of Hankel matrices. And now we come to the main steps of ASPIRA2 algorithm. So we use the same input information. And we compute also DFT vector, and we use again a AAA algorithm, but only in order to find the M, because it is number of iteration -1, and to find parameters for this Lowner matrices. But we do not go further into this barycentric formula. Now nodes Zj and the coefficients gamma j are reconstructed in different way. So to find the Zj, we have to consider the following matrix pencil and to find the eigenvalues of this matrix pencil. And in order to find coefficients gamma j, we have to solve the following system of linear equations where it is van der Mon matrix. And so now when we compare this ASPIRA2 algorithm with Prony-type algorithm, so we see that the step where we reconstruct gamma j, it is the same. Then when we reconstruct Zj is very similar, just the only one difference that we have Lowner matrices. And for Prony-type algorithm, we have the Hankel matrices. And parameter m, the order of the exponential sum is reconstructed differently. So in ASPIRA, we reconstruct it in the AAA algorithm. It is like number of iteration -1. And in Prony-type methods, we we find this M, so we have to create this big Hankel matrix and to find the numerical rank of this Hankel matrix. And now I would like to go to the last part of my talk. So I would like to show you that our new ASPIRA algorithm can be very good applied for the reconstruction of exponential sums and also for the question of construction of exponential sums of good approximation for some special functions. And I also like to compare performance of ASPIRA with matrix pencil method. It is one of the Prony-type methods, and I use here only matrix pencil method. So I would like to do some remarks first. So for the reconstruction of exact data, both or three of these algorithms give very good results, and they work equally good. So therefore, I will not speak about reconstruction of exact data in this talk. And then matrix pencil method works the best when we put L equal to N. So L, it is the order, it is this upper bound for the order of the exponential sums, but it is not equal N in general case. And then we found out that ASPIRA gives a better result for the reconstruction of noisy data. And for some examples, it gives also for some spatial functions, it gives also better results for the construction of good approximation for some spatial functions. And I also like to notice that for computations, we use only double precision. So I will start with reconstruction of exponential sums with noise, with given noisy data. So we have this exponential sum of order 8, and this exponential sum is given by the following two sets of parameters. So this is coefficients, and this is frequencies, because this is points from the unit circle. And as an input data, we take the following values. So it is values of function f corrupted with some noise, and noise is, for this example, noise is really big, I have to say, and we take uniform random noise. And we take really a lot of input samples, 800s, and we take for MPM also n equal L, so MPM cannot work better. And so we get the following reconstruction results. So at these pictures, this black function, this black line, it is for both pictures. It is the original signal f. Now this red points, it is this input information, it is this values yk, so functions plus noise. And at this picture, we see how MPM works, how matrix pencil method works. So this blue line, it is reconstructed signal with the use of matrix pencil method. And at this picture, this pink line, it is reconstructed signal with the use of ASPIRA tool. So if you compare these two pictures, you can see that for this example, ASPIRA works so really better. So now I would like to go to the question of constructions of good approximation for some spatial functions. So first, we consider the function 1 over t, but we modified this function a bit because we take only the segment 0, 1. And we construct exponential sum of good approximation of order 5 using two algorithms, ASPIRA and MPM. And we take n equals 60, so 120 function values, but now not at integer points because we have only the segment 0, 1. And for MPM, we use L equals 30. And at this picture, you see the following error of approximation. And red line, it is for MPM, and the blue line, it is for ASPIRA. So you see here what results we get. It is 10 to the power minus 9 or minus 10. And so we can say that in general, both this algorithm work very good for this simple function. And here I also would like to notice that this question of construction of good or best approximation for the function 1 over t is very well studied. So there are papers also Brest and Hackbusch and also Kamler, and they mainly use the so-called Remetz algorithm for the construction of exponential sum of good approximation. And this Remetz algorithm is based on minimization of L infinity norm, of maximum norm, and is performed only with higher precision. And with our ASPIRA, we get results that are really very close to the results that one can obtain with Remetz, although ASPIRA is not based on minimization of some norm in time domain. So now we consider the Bessel function. So here I would like to notice that we take this example from the paper of Belkin and Manzoun, and they also consider this question of construction of good approximation for some special function. So we take this example. So Bessel function on the segment 0, 100 pi, and we construct a best approximation with the use of, again, ASPIRA and MPM. So we construct a best approximation or good approximation of order 28. It also comes from the paper of Belkin and Manzoun. And we use the following input data. So we take n equal 515. So it is 130 function values. And for MPM, we use L equal 300. And we get the following reconstruction results. So it is again this arrow in the logarithmic scale. So red line, it is for MPM, and the blue line, it is for ASPIRA. So again, both algorithm works quite good for this function, for this Bessel function. And I also would like to notice that with ASPIRA, we get exactly the same results that obtain Belkin that were obtained by Belkin and Manzoun in this paper for this function. Now I come to the last example. So we consider this function. It is the Dirichlet kernel, and we take only half of the period. So we take Dirichlet kernel of order 50. And we construct exponential sum of order 44. So we employ the following input data. So we take n equal 1000. So it is 2000 function values. And for MPM, we take L equal 1000 also. So n equal L. So MPM cannot work better. And we compute this exponential sum of order 44 using ASPIRA and the MPM. This is the arrow here that we got with the use of ASPIRA. So it works very good. It is 10 to the power minus 13. And this is the arrow that we got with the use of MPM. So it actually means that MPM fails for this example. And it happens at the very last step of the algorithm where we compute this coefficient gamma j. So reconstruction of nodes, or this parameters lambda j, works almost equally. So MPM gives also somehow good results for reconstruction of nodes. But then when we want to reconstruct coefficients gamma j, for MPM, we deal with van der Monde matrices that are ill-conditioned for this given information. So we have here really a lot of function values, and we have really large order of the exponential sum 44. And probably the main point here is that, so if you remember, when I was talking about this function in the beginning, so for the Dirichlet kernel, we use these nodes e to the power lambda j that are located inside and outside of the unit circle. And for this input data, van der Waals matrices are ill-conditioned, and therefore reconstruction of coefficients gamma j fails. But when we deal with ASPIRA, we deal with Cauchy matrices at this last step when we want to reconstruct gamma j. And these Cauchy matrices give us this good approximation results. So that was the last example. And now I would like to do some conclusions in the end. So we develop this new ASPIRA algorithm for the reconstruction of exponential sums. And the main idea of our new algorithm is that that Fourier coefficients or DFT coefficients of exponential sums have a rational structure, and we can reconstruct this rational structure using a known numerically stable AAA algorithm. And we show also that there is a connection between ASPIRA and Prony-type methods. And we show that ASPIRA can be described as a matrix pencil method. And we also show that ASPIRA works better for some examples when we deal with noisy data, and it works also very good in the question of construction of exponential sums of good approximation for some special functions. And here are our publications on the topic. So the results that I presented you today, I took from this our preprint. So it is almost ready. It's not on archives yet, but I think maybe we'll submit it this week. And in this talk, I was only speaking about the case when we have these parameters lambda j pairwise distinct, but it may happen also that they come with multiplicity, and in that case we deal with this extended exponential sums when we have this polynomial coefficients. We also considered that case, and these results can be found in this preprint. And the last publication, it is our first publication in that direction, where we presented this idea, reconstruction of exponential sums using rational structure of their Fourier coefficients. And in this publications, we considered only real exponential sums. So thank you for your attention.
All right, thank you very much. Everybody smash that reaction button. And Justin can stop the recording.